Hello and welcome to another Carbon tutorial. In this video, I'm going to explain a technique to speed up your workflow that we call Physics LOD. First, you iterate on a low resolution simulation and get it approved, and then uprez the simulation, maintaining the look but with the physics fully active. Let me show you how to set this up, and then at the end I will show you it in action on a real garment. So let's get started. First of all, let me reiterate what the GoSkin parameters do. The main parameters are here: strength, viscosity, and now with version 3.0 we also have trail stiffness and trail viscosity. Strength does the same thing as it does before. The strength provides a maximum strength value which controls the snapping of the points to animate positions under small deviations. So if you're pretty close to your goal, and the strength just brings in the final snap basically. The viscosity helps cope with fast motions. It ejects part of the goal post animation into the pre-dynamic update of the internal solver so that the cloth can basically keep up with it. Next up are the new parameters. Viscosity is the easier one. It's just like viscosity that we find up here if we go to bend viscosity or stretch viscosity. It's a viscous ratio, and per default you are pretty good setting it just to 2 or 4. Trail stiffness controls the response of the goalpost under large deviations, so this now complements strength. Alright, let's get started. So what do we have here? Our first simulation here is our low-res simulation. I'm going to show you the mesh. And it only has about 926 triangles in here. So I'm just going to run this and you see what it does. Reset the simulation, press save, and let's go. So what it does, it has an animated welding, and kind of like curtains, it opens and closes. And you can see the general behavior as we're getting folds. Let me pause it somewhere here. You can see, especially if we go here in the beginning, we got roughly 4 folds. 1, 2, 3, 4. So this is our behavior that we want to target. 4 folds here in the beginning, and then just open and closes nicely. Again, if you go to the end, 4 folds. 1, 2, 3, and then here we got the 4th wiggle. All right. Now, when we just run a high-res simulation, and I've prepared one here for you already, and you can see the mesh, which contains 22,168 triangles. So it's quite a lot larger. It's like 25 times larger or something. If you just run a simulation with exactly the same parameters, and I had 10 iterations, 10 subdivisions, the first thing we're going to notice is when I run this, it's going to stretch more, because we need more conversions to help enforce the limits. So I'm just going to now have to up it to 20. Both of them. Reset, and now it should stretch less. All right, that's better already. So besides slowing us down through having more triangles, we also have to slow down simulation by adding more iteration and subdivisions. But let's say time is not the essence here. What we want to do is just do a high-res versions of the curtain. And as you can tell, if I scrub here, since we have much higher resolution, we end up with much finer wrinkles here. So the folds are much smaller, again comparing to the other one where we have here coming in 4 folds nicely, and then go back to the high res, we have countless folds. So you can't just simply increase the resolution of the cloth and get a higher res version that preserves the main shape. And this is really the target of this tutorial here, where we're like, okay, we have 4 folds, but this is obviously very low res and coarse. How can I make this higher res but preserve the general look of it? So I want to keep 4 folds. I do not want to go to this high res where I have like 20 folds or something. Okay, let's have a look now. The first thing I need to do is to create a goalpost. How am I doing this? Well, I'm taking my low res simulation here, so the output of the simulation, and I'm taking the low res starting position and then the high res starting position. And this allows me through the mesh deformer to create a geometric deformation of the high res based on the output from the low res simulation. And you can see here, that's the result we get. We got the 4 wrinkles, but with higher resolution. And I purposely kept the deformer type to skinning, so we can see the very crunchy look because it closely matches the low res. Obviously, that's not what we want. That's not the purpose of high res, just to have the crunchy folds and high resolution. We want a smoother behavior. But this is our target now. All right, we're now going to inject this into the simulation, which is the same as the high-res simulation, with the difference now that we have goalposts that we can enable. First of all, I'm going to start it with 0. And if I just reset the simulation and kept it to 2020, would receive the same. So if I set this to 2020, run the simulation again, we end up with the same result because goalposting is basically inactive. I need to set some parameters on the goalpost for it to do something. But what you can already see is the lines showing how much our current simulation deviates from our goalpost. You can see, especially in the corners, it deviates quite a bit. So now let's go ahead and add some goalposting. I'm going to the cloth, and we're going to try it out to tune this in the correct order that Numerian recommends. The first step we recommend is actually tuning the trail stiffness. The trail stiffness, remember, is under large deviations. So you want to make sure that our simulation follows the goalpost, but not too tightly. Let me show you what happens when you do it too tightly. So I'm going to set it to 10 now, reset the simulation, and play. We can already see after a few frames that we follow it very tightly. You only see dots, you do not see lines, means there's no deviation, but that obviously also means that we preserve the crunchy look from the goalpost, which we don't want because it shows the geometry of the underlying low resolution animation. So now let's just keep reducing trail stiffness by a factor of 10 until we can see a pleasing result. Let's go to 1, reset the simulation, and play. Now this is already a bit smoother, but let's see what happens. Okay, it still looks quite crunchy. We can stop here. Let's go down by another factor of 10 to 0.1. Resetting simulation, and let's run. All right, we're still meshing pretty tightly as I do not see a lot of lines. I still see the dots. Now we're getting some more lines, but I think it is still getting a bit crunchy here. Yeah. So going somewhere here, we can still see the crunchiness here. So let's reduce it by another factor of 10. 0.01. And run the simulation. Okay, we're definitely getting more deviation now as you see the lines. This is starting to look really smooth. We can also tell that we're preserving the overall shape, so we do not have a lot of deviations, but just enough to actually smooth out the crunchiness from the low-res simulation. That's pretty good. Let's see what happens if we go by another factor of 10. So 0.001. Now we're starting to see a lot of deviation. And once this one now comes together, we're going to see that actually we're now not preserving the 4 folds. You can see we have more than the 4 folds, so we have way too many and we're not preserving the overall shape. So I'm going to just reduce a 0 here. All right, because the previous side was actually quite nice. Next up, we can set the trail viscosity to 4 as a default parameter. 2 or 4 is fine, I stick with 4. We have the strength and the viscosity left. First of all, we want to set the viscosity, which you can also set automatically. The viscosity injects some of the motion of the target animation, so the target goalpost, into the pre-dynamic update. So how can we calculate a good value? So think of it as a percentage of the overall frequency of the simulation. So what's the overall frequency? In our scene here, if I go down here, we are at 24 frames per second, so 24 FPS. That's our timeline frequency. And on our simulation, we have 20 iterations and 20 subdivisions. I'm actually going to decrease them because the goalposting helps us fight some of the extension through gravity. So I can go back to your original simulation settings, which gives us a bit more speed back. So now we have 10 subdivisions. Remember, we had 24 FPS and 10 subdivisions. So internally, our solver is 240 Hertz, is 24 times 10. We recommend applying about 10% for the viscosity. So 10% of 240 is 24. I'm going to put 24 in here now. You will not see too much of a difference in the scene because it mainly helps with very fast motion and this is a quite slow motion. But it's always good to inject it. If you have very fast scenes, you might want to apply more than 10%. You want to go up to 20, 30, 40, 50, 60 and so on. You should not go above 100%. So you should not go in this case above 240 because you will inject too much motion, which can lead to overshooting and oscillations. Okay, let's run the simulation. This still looks good. As I said, we have very slow animation here, so we probably could even get away with less viscosity, but I'm happy with it. Now what we want to do is to tweak the strength. The strength is currently set to 0. Similar to the trail stiffness, we can start with a large number and see what it does. Reset the simulation and run it. And I can already see at 10 that we're going to get crunchy behavior here. Do you see this? It's quite crunchy down here. Yeah, you can definitely see the tessellation of the lower res coming through here. So 10 is too high. Let me go to 1 and see if it still comes through. So I cannot see it coming through, which is quite nice. So I think 1 is fine then. If I cannot see any negative effects at this point, I'm going to stick with 1 and everything follows nicely our low res. We can definitely tell here nicely, and let me look at the output mesh, that we have the 4 major folds up here. 1, 2, 3, 4, but we have very smooth behavior. We do not see the patterns from the underlying geometry. And we can compare this to the other examples. So here's the original. Here's what we have now. It's a high res, so obviously we get nicer folds up here because we have more fine material that's bunching. But the main folds here, the main features are preserved, as you can tell. Plus we're adding a little bit of extra behavior, a little bit of believable high res details. Compare this to the original high res, where we have just a lot of folds down the line and it's nothing compared to the input. Okay. Now you might ask the question, well, what if I just ignore the new trail parameters and stick with the original, just strength and viscosity? Well, we can have a look at this now as well. So keep in mind, this is the result we're getting right now with our trail stiffness and our strength. I'm going to show you can get very similar behavior in this scene, but I will also show you another scene in a bit where it definitely makes a difference having the trail stiffness versus just increasing the strength. Let's go now to the scene. This one again is a bare bones copy of our high-res simulations, but I have iterations and subdivisions set to 10. Now go to a goal posing and I'm going to enable it here, and my viscosity I set to 24, which is 10% of the internal scene frequency. So 0.1 times 24 times 10 is 24. Perfect. Now, just as before, we're going to tune the strength to make sure it's strong enough to hold things up, but we do not want it to be so strong that it makes the underlying artifacts basically appear, the crunchiness, as I call it. So we started here in the previous one with 10, and which was way too crunchy because combined with the trail stiffness, it really was strong and showed the underlying texture of the low res. Now I'm going to start with 10, and I'm expecting, since we do not have trail stiffness, to be actually much better behavior than with the other one. So let's play. And here we go. You can see it matches quite closely down here and it gives up top. You can see some of the crunchiness in here, but it's not as bad as with the other one. Let's go to somewhere here and compare it with the previous simulation, where we can definitely tell it's much smoother, or showing you the output mesh. So this is our trail stiffness tuned. Now this is our current one. We can see crunchiness is here. So let's reduce the strength then. Let's halve it to 5. Reset the simulation. Let it calculate to the frame. And we can see that it's a bit smoother, but still not perfect. But what does the simulation look like? Okay, we are still not seeing too much crazy extension. We're seeing it follows the goalpost mostly. Let's go here higher. And we still have mainly our 4 folds, but we're starting to lose a little bit of it. So if we go down and set it to 1, just as we had for the other one that also had this trail stiffness, let's see what we get here. Now I can definitely see a lot more lines already, so we're not following as closely. What we're missing is the trail stiffness that helps with these large deviations that we have here in the side corners. In order to really make it match again, we have to up the strength. But as you saw, if we up the strength, we're going to see some of the crunchiness. So let me compare again the output of this here, the output of that, and it's probably easier if we go to somewhere here where we have the folds nicely. You can see there is more freedom and more extension in the right one, but we're matching the original less. And I have a switch here which allows you to compare all of them. So here's the original, here's the high res. Let me move this one up so we compare the other ones easier, because this one obviously doesn't match it. Original, here's with the trail stiffness, and here is with the strength only, no trail stiffness. We can see here that we have more elongation than when we combine it with the trail stiffness. You can see it's a little bit more elongation. But again, we cannot really go up much more in the strength, because otherwise we're going to see the artifacts on here. So you probably can maybe try 2 or something to see if you can improve slightly. Okay, now we're matching a little bit more. Let's compare 3 to 2. So these are actually pretty good match. And so now we have a relatively comparable setup, but you can see we give up a little bit more here. This is where the trail stiffness would come in. But actually it's not bad, and I think it's good enough. So this is how I would set up this scene using the new trail stiffness parameters, or if you don't want to use it or have an old version, you can set up the strength and the viscosity. Now I'm going to go to a different scene where I will show even better how trail stiffness is very important in order to match your target animation from the go pose. Let me show you. It spins in one direction, and at frame 150 it starts turning around and spins in the other direction. You can see the binding helps it stay in place up top. And especially down here, you can see there's very beautiful behavior, and we have 1, 2, 3, 4, 5, 6 distinct folds, a bit like a sunflower. Looks very pretty. So we want to replicate this. Now if we go and just, same with the other one, take our circle and put a higher res mesh on it, and here we have 14,500 triangles, and run the same thing again, what you will find, as you expect, you get much finer folds and you do not get the same behavior. So looking from the top, we already see there are much more folds. The other one was 6, and now we have more. And if it spins here, it's also a nice, beautiful pattern, but we do not have this sunflower style pattern, which my target is here to replicate, but uprez it. So just as with the other simulation, we're going to look at tuning the goal skin parameters to drive a high-res simulation that nicely captures the overall look and behavior of the low-res. Let's get started. I have a copy of the high-res, and just as before, I'm using a carbon mesh deformer to create an animated version of the high-res that follows the low mesh. This is just a geometric deformer, and as you can already see, just as before, because I'm using the skinning type for the purpose of this tutorial, you can see the crunchiness here coming through, so the low-res pattern really shows through heavily. To save some time in this tutorial, I have already tweaked the parameters for the trail stiffness in here. We needed more trail stiffness to keep up with the fast motion. Let me just overlay the low resolution simulation here, and then we can compare how well our goal post simulation matches the low res. There's a good capture. You can see here too. It's nice, and we add a lot of details to it. So here is the low res and the goal post. You can see that we capture the existing folds, but we high res on top of it. And here we have our distinct sunflower pattern. Go up, we very neatly captures it. We get our overall silhouette here is very well preserved. If, for example, you look at this edge, it's nicely preserved, but we're getting the believable high-res extra details up here where it wraps and folds around. That's what you want. Now, let's go to a final step. Again, we have a third simulation, and this is where we're going to try to tune it without the trail stiffness, and it will become very clear why trail stiffness is actually needed in this case. So let's start again, 24 viscosity. And I already have a strength of 20 set here. Let's see where this leads us. So strength of 20. We can see a little bit of the crunchiness, but not too much. If we go up a higher strength, and I can show you this easily, for example, 100, we just need to simulate a few frames where it falls down. You can very much now see the crunchiness, the low-res texture, the resolution really shows through. Even if you go down to 50, and let me reset this, you can already see at 50, this is still there. 20. 20 is just about bearable, I'd say. So we should not use a strength higher than 20. But now what is the problem? Well, let me simulate and see where we get to. You can already see here a lot of trails because we don't have trail stiffness. When you look at something like this, you can see we're deviating quite a bit from our original silhouette. So if I shown wireframe the original and the output from this one, we're quite shorter here. So we're deviating, we're not preserving it as much. And if we go on, here becomes even more evident. We're actually trailing quite far behind and the overall shape is now quite different. So we can't increase the strength much more because we already maxed out our strength before it starts looking too crunchy in the beginning. As we said here, we need to have a maximum of 20, ideally lower, but let's say 20 is a semi-safe value that we can live with. But how can we make it follow here now? Well, you say, what parameters used to follow the motion to inject some of it? Well, viscosity. So let's increase the viscosity, and let's just go for the maximum is 240. So it's the FPS, again 24. Our simulation has 10 iteration subdivisions. So maxing out our viscosity, we can't go above that because otherwise you're going to inject too much motion and you get other visual artifacts like oscillations and overshooting. So I'm going to reset the simulation now and see how closely we capture it. What you can see is that we're much closer now, but we're still not perfect. But I can't go much further because now we're already gonna overshoot injecting too much motion. You can see here that we're now ahead of this and we're starting to deviate. There we go. So if you compare this and to our trail stiffness, you see how much closer we are by using trail stiffness. This is without trail stiffness, and here we have our trail stiffness set up. When we really have the high fast motion where things are gonna start to vastly fall apart, this is where trail stiffness helps bring it in. And without trail stiffness, viscosity alone can't do it. So this is why I would really recommend using trail stiffness and tuning your parameters as I showed. One topic I just want to quickly pick up again is the topic of the mesh deformer. So the mesh deformer is creating our goalpost for our high-res simulation. And as mentioned before, it takes the low-res geometry and deforms the high-res geometry. And I have purposely chosen the skinning deformer type because it gives us a very accurate matching of the lower res. And in this case, because there's such discrepancy between the high res and the low res, it shows through the low res tessellation. So we can see the crunchiness, as I called it. So the reason why I'm doing this in this tutorial is that it's very obvious then when we tune the stiffness and the strength parameter on the goalpost for the cloth, if it's too strong, we will match this too closely and we know that we need to loosen up the parameters. But in a real life scenario, what you want to do is you want to get a goalpost that is smooth and beautiful, so you have an easier way of tuning your parameters. So for example, in this case, instead of using the skinning deformer type, I would use the smoothing deformer type. So changing from skinning to smoothing, you can estimate the radius to get a good starting point, apply estimate, and update mapping. And we can see now that we have a much smoother deformer. And if you think that's maybe too much, too smooth, we can just reduce the radius and update again. And as we keep reducing, you can see that it's going to match more and more the result from the skinning. So maybe 0.2 is a decent result, because the better quality your goalpost is, the better quality your resulting high-res simulation will be as well. Before I finish this tutorial, I just want to quickly show you an example that's closer to what you might encounter during production. So we will find a garment and an animated character that is a more realistic example rather than these simplified tutorial scenes. Here we have an example of a jumpsuit. The jumpsuit runs in a low resolution here on the screen right now, and this is only around 7,000 triangles. And you can see it's got a decent behavior, and we like the overall folds, especially those around the collar and the torso. But now that we've run the low res resolution, we want to try to uprez it. So let's look at the uprez version now. And now we have the high res version. And it preserves all of the major folds up top around the neckline, the torso line, and on the legs, but it adds a lot of believable high-res details to just really upscale believably and make it stand apart from a simple geometric upscale. Because as we all know, if you just use a geometry deformer like a carbon mesh deformer to capture a low resolution for high resolution, you do not A, create the extra details, and B, you do not preserve the collision correctness. While here we run full collision resolution, so the high res will collide but not self-overlap as you get with a lot of the deformers, because it's just geometric and not physical. And here's a little close-up. You can see the slider going back and forth, revealing the high res versus the low res. And there's a stark difference in resolution, but the overall fold shape is preserved and finer details are being added in the high res to make it a believable high resolution mesh. Thank you for watching, and I hope this approach can help you achieve faster turnaround time and great results. Thank you so much.